Section: Introduction. In this section, we delve into the crucial decision-making process involved in gradient-based optimization, particularly focusing on the selection of the learning rate, also known as the step size. If the learning rate is too small, the learning process may be sluggish, or the model could get stuck in unfavorable areas of the loss landscape. Conversely, if the learning rate is too large, the training process is likely to diverge. To address this challenge, practitioners often opt for a dynamic learning rate schedule denoted as ADA_T. Modern deep learning frameworks commonly incorporate a warm-up phase in the learning rate schedule. During this warm-up period, the learning rate ADA_T gradually increases from 0 to a specified target value ADA_text TRGT over a warm-up duration T_text WRM. Following the warm-up phase, it is typical to decay the learning rate, for instance, using a cosine decay schedule. Understanding the rationale behind warm-up is crucial for practitioners, as it plays a significant role in optimizing the training process. Various explanations have been proposed to justify the use of warm-up. One perspective suggests that at the start of training, when the network is initialized randomly, the gradient steps are not meaningful. Therefore, it is advisable to take smaller steps initially to prevent large deviations. Another viewpoint highlights that warm-up helps in limiting the weight update magnitudes in deeper layers, thereby averting significant instabilities. Additionally, warm-up is believed to be particularly beneficial for adaptive optimizers like Adam, as it aids in reducing the variance of the adaptive learning rate during early training stages. From a broader perspective, warm-up is seen as gradually reducing the sharpness of the loss landscape, allowing the model to transition from poorly conditioned regions to flatter areas that can accommodate larger learning rates. Our research focuses on investigating the impact of learning rate warm-up across various architectures, datasets, and optimizers. Through systematic experiments, we demonstrate that the primary advantage of learning rate warm-up lies in enabling the network to handle larger learning rates effectively. By dissecting the effects of warm-up duration and target learning rate, we shed light on its significance and extend our findings to adaptive optimizers and transformers. In our analysis, we identify distinct phases and mechanisms influenced by the network's initialization and parameterization. Notably, the network's performance is heavily influenced by the target learning rate, with increased warm-up time offering marginal benefits by maintaining the network stability. By enhancing the network's tolerance to higher target learning rates, warm-up facilitates more robust hyperparameter tuning, thereby enhancing training efficiency. Our investigation into Adam Optimizer reveals similar underlying mechanisms as in SGD, albeit with a focus on preconditioned sharpness. We introduce a modified initialization approach for Adam, termed GI Adam, which mitigates instabilities and enhances performance by reducing the preconditioned sharpness. Furthermore, our experiments highlight the potential for optimizing warm-up time by leveraging the catapult mechanism to estimate the initial sharpness scale effectively. This approach allows for a more informed choice of the initial learning rate ADA_text init, potentially reducing or eliminating the need for a prolonged warm-up period. Section Summary. In this section, we extensively study the impact of learning rate warm-up across various architectures, datasets, and optimizers, demonstrating that the primary benefit of warm-up is enabling networks to handle larger learning rates effectively. Our experiments reveal that the duration of warm-up has minimal impact compared to the target learning rate, which significantly influences network performance. For Adam Optimizer, we introduce GI Adam, an alternative initialization method that reduces preconditioned sharpness, enhancing stability and performance, ultimately leading to improved training outcomes. Section: Notations and Preliminaries. In this section, we will discuss the notations and preliminary concepts related to sharpness, adaptive optimizers like SGD, and Adam, linear warm-up, parametrizations in neural networks, and the self-stabilization mechanism during training. Sharpness is defined as the maximum eigenvalue of the Hessian of the loss function at a specific training step. For adaptive optimizers using a preconditioner, the precondition sharpness is calculated similarly but with the preconditioner matrix involved. SGD, M, is a stochastic gradient descent method with momentum, where the parameters are updated based on the gradients, learning rate, and momentum coefficient. Adam, on the other hand, updates parameters using gradients, learning rate, and the first two moments of the gradient with specific coefficients. Linear warmup involves gradually increasing the learning rate from an initial value to a target value over a specified number of steps. The choice of initial learning rate in linear warmup is crucial and will be discussed in the section on learning rate initialization. Different parameterizations in neural networks, such as standard parameterization, SP, and neural tangent parameterization, NTP, play a significant role in training dynamics. The maximal update parameterization, MUP, is also proposed for feature learning at infinite width. The self-stabilization mechanism during training is closely linked to warm-up and training instabilities. When the learning rate surpasses a critical threshold, training can either stabilize through a self-stabilization process or experience severe instabilities leading to training divergence or failure. The critical threshold is related to sharpness, and the self-stabilization process involves 4 steps to restore stability and allow for loss decrease. While the self-stabilization process may vary for different optimizers like SGD with momentum or Adam, a similar qualitative mechanism is observed in practice. The critical learning rate is influenced by various factors like the choice of optimizer, mini-batch size, and model properties. Section Summary. In this section, we define the sharpness as the maximum eigenvalue of the Hessian of the loss at a given training step, and introduce the concept of preconditioned sharpness for adaptive optimizers. We discuss stochastic gradient descent with momentum, SGDM, and Adam optimizers, detailing their update equations and the impact of learning rate adjustments through linear warmup. The section also explores the relationship between warmup mechanisms, training instabilities, and the self-stabilization process, highlighting how the critical learning rate influences training dynamics and stability in various optimization algorithms. Section: Warm-up mechanisms of gradient and adaptive methods. In this section, we analyze the underlying mechanism of warm-up in terms of training instability. We found that there are cooperative and competitive dynamics based on how sharpness evolves with training instability. When it comes to stochastic gradient descent, the learning rate warm-up is closely linked to sharpness dynamics. The sharpness determines the instability threshold, denoted as eta_c. Increasing the learning rate during warm-up can trigger training instabilities. If the warm-up rate is not too high, these instabilities cause a temporary increase in loss and a decrease in sharpness. This helps to restore stability through a self-stabilization mechanism, enabling the model to adjust to the higher learning rate. The main aim of warm-up is to gradually decrease sharpness, guiding training towards flatter regions that can handle higher learning rates. However, during training, there is a natural inclination for sharpness to evolve. Before surpassing the instability threshold, eta less than eta_c, training naturally experiences either a rise or fall in sharpness, which is unrelated to warm-up. There are 2 main scenarios that can occur during training: natural progressive sharpening and natural sharpness reduction. In the progressive sharpening case, the network naturally increases sharpness while the learning rate is also increasing, leading to a cycle of instability and stability. On the other hand, in the sharpness reduction case, the network is already reducing sharpness, and increasing the learning rate can cause instability, requiring more training steps to restore stability. There is also a scenario where sharpness remains constant throughout training. The duration of warm-up plays a crucial role in how training progresses. Increasing the warm-up duration delays the point at which training exceeds the instability threshold, allowing sharpness to evolve freely. This can result in smaller and delayed instability cycles, enabling training at higher learning rates without divergence. The type of initialization, whether small or large, also impacts the warm-up mechanism. Small initializations tend to start in flat regions and benefit less from warm-up, while large initializations undergo early sharpness reduction and benefit more from warm-up. Large initializations can eventually transition to progressive sharpening, especially with prolonged warm-up periods. Instances of constant sharpness typically occur in models operating near the lazy regime. Section Summary. In this section, we delve into the mechanisms of warm-up in gradient and adaptive methods. We discover that warm-up plays a crucial role in guiding training towards flatter regions to accommodate higher learning rates by reducing sharpness. The interplay between the natural evolution of sharpness and warm-up interventions can lead to cooperative or competitive dynamics, influencing the training process significantly. Section: Stochastic Gradient Descent with Momentum, SGDM. In this section, we will discuss stochastic gradient descent with momentum, SGDM, and adaptive gradient methods, ADAM. When using SGDM, we notice that during early training, the loss may decrease in a nonlinear way when momentum is added, even with small learning rates. This can make it hard to distinguish between the effects of warm-up and the natural momentum-induced fluctuations in loss. The instability threshold eta_c changes during training, starting at nicefrac 2, lambda_h_0, and evolving to nicefrac 2 plus 2 beta, lambda_t_h. The late time instability threshold is influenced by the batch size, leading to challenges in analyzing the training dynamics of SGD with momentum. However, the basic warm-up mechanisms are similar to vanilla SGD. Moving on to ADAM, we observe that the stability of adaptive optimizers depends on the largest eigenvalue of the preconditioned Hessian, denoted by lambda_p_-1h, rather than sharpness itself. The preconditioned sharpness starts high and decreases during early training, which can lead to training failures if not handled properly. Strategies to improve ADAM's initialization are discussed in the paper. We then explore the impact of warm-up on training and generalization. We find that generalization capability is mainly influenced by the target learning rate eta_text TRGT, and ADAM is sensitive to large learning rates. Increasing the warm-up duration helps the network handle larger target learning rates and improves generalization slightly. Our experiments involve training wide res nets, WRNs, and transformers on various tasks using SGD or ADAM optimizers. The training process includes a warm-up phase where the learning rate increases linearly from an initial value to the target value over a specified number of steps. After warm-up, training continues at the target learning rate. We also gradually decrease the learning rate using cosine decay in some cases. Training failure is defined as a significant lack of improvement in performance compared to the initial value. Section Summary. In this section, we summarize the differences between stochastic gradient descent with momentum, SGDM, warm-up and vanilla SGD, highlighting challenges in distinguishing warm-up-induced catapults from momentum effects. Additionally, we explore the evolution of instability thresholds during training, noting significant influences of batch size on late-time instability thresholds. Furthermore, we delve into the impact of warm-up mechanisms on the training dynamics of adaptive gradient methods, ADAM, emphasizing the importance of warm-up in preventing training failures and improving generalization, particularly for large learning rates. Section: Stochastic Gradient Descent, SGD. In this section, we present findings on stochastic gradient descent, SGD, based on heat maps showing the best test accuracy achieved during training. These heat maps are plotted in the eta_text TRGT, T_text WRM plane for different parametrizations and loss functions. They illustrate the relationship between warm-up duration and the maximum trainable eta_text TRGT, highlighting the convergence-divergence boundary. We observed that a longer warm-up duration supports training at higher target learning rates, especially beneficial for large initializations and mean squared error, MSE, loss. On the other hand, the advantage is less significant for smaller initializations like μp and when using cross-entropy loss. The increase in maximum eta_text TRGT with longer warm-up durations can be explained by the milder loss catapults observed as warm-up duration increases. Our analysis indicates that the final performance primarily relies on the target learning rate rather than the warm-up duration. Models with large initializations benefit from increased warm-up duration, enabling training at higher learning rates. In contrast, models with flat initializations can already achieve optimal performance without warm-up, although extending the warm-up duration broadens the range of optimal learning rates. We conclude that warm-up plays a crucial role in improving model performance for large initialization cases and expanding the range of optimal target learning rates for small initializations. Additionally, we demonstrate in the appendix that these results hold when incorporating momentum and cosine learning rate decay. Moving on to Adam, we found that warm-up in Adam enhances training at higher learning rates by reducing the severity of catapults, which can lead to performance degradation and training failures. Unlike SGD, models trained with Adam tend to exhibit training failures rather than divergences, often due to vanishing gradients in certain layers. In Adam, test accuracy decreases before reaching the failure boundary, contrasting with SGD where optimal learning rates are near the divergence boundary. This difference is attributed to Adam's memory of gradient magnitudes, which can lead to challenges in escaping high-loss regions. Therefore, a longer warm-up is more beneficial for Adam compared to SGD to avoid training failures. Section Summary. In this section, we present heat maps illustrating the impact of warm-up duration on training dynamics using stochastic gradient descent, SGD, and Adam optimizers. The results show that longer warm-up periods facilitate training at higher learning rates, with the final model performance primarily dependent on the target learning rate rather than the warm-up duration itself. While SGD benefits from warm-up by improving performance in large initialization cases, Adam's vulnerability to large catapults is mitigated by warm-up, preventing training failures and performance degradation. Section: Improved hyperparameter initialization schemes for optimizers. In this section, we improved hyperparameter initialization schemes for optimizers. When it comes to selecting the initial learning rate for warm-up, it's common to set it to 0. However, our analysis shows that starting with ADA_text init equals 0 may not be the best choice because it can delay the learning rate from reaching the desired level quickly during warm-up. We found that setting ADA_text init equals ADA_C, where ADA_C is the initial critical learning rate, is more effective. To estimate ADA_C, we developed a simple search method that only requires forward passes. This method involves an exponential search followed by a binary search to narrow down the interval containing ADA_C. By setting ADA_text init equals ADA_C, training can reach the target learning rate sooner. We also introduced a modified warm-up schedule that helps achieve the target learning rate faster. This schedule adjusts the learning rate over time based on the initial critical learning rate ADA_C. By considering the computational cost of estimating ADA_C and the number of forward passes required, we can calculate the net computational savings. Additionally, we proposed GI Adam, which improves the Adam optimizer by initializing the second moment using the gradient squared. This initialization method reduces the initial sharpness, preventing training failures at large learning rates. GI Adam shows consistent improvement over standard Adam and pushes the training failure boundary to higher target learning rates. Further exploration of different initializations for Adam, such as v_0 equals a_g_0 to the power of 2, could lead to even better performance. Section Summary. In this section, we introduce improved hyperparameter initialization schemes for optimizers, focusing on setting the initial learning rate for warm-up. We propose setting the initial learning rate to a critical value, ADA_C, to induce loss increase and facilitate achieving the target learning rate earlier, leading to computational savings. Additionally, we present GI Adam, a variant of Adam that initializes the second moment using gradients, reducing preconditioned sharpness and preventing training failures at large learning rates. Section. Towards parameter-free warm-up strategies. In this section, we explore a potential warm-up strategy called persistent catapult warm-up, which aims to improve training without needing specific parameters. The main idea is to use repeated catapults to gradually reduce sharpness, making it easier to train at higher learning rates. The strategy involves starting at a stable reference point and estimating a range containing a critical learning rate. Then, a catapult is induced by increasing the learning rate to the upper limit of this range. Training continues until the loss drops below the reference point, at which the new point becomes the reference. This process repeats until the target learning rate is reached. The initial stable reference point is the model starting point. The persistent catapult warm-up allows training at higher learning rates without a set warm-up duration. By using the sharpness indicator, it automatically adjusts the warm-up rate based on local sharpness information, creating an adaptive warm-up process. This adaptive method removes the need for manually setting the warm-up duration, making the warm-up more efficient. Although the persistent catapult warm-up is promising, it requires specifying the size of the catapult, adding another hyperparameter. However, it inspires the development of parameter-free warm-up strategies to simplify training. Further exploration of parameter-free warm-up strategies is left for future research. Our analysis sheds light on the importance of warm-up in optimizing training and parameter settings. Warm-up primarily helps train at higher learning rates and stabilizes training dynamics to prevent divergence. We identified various underlying mechanisms and suggested improvements for hyperparameter initialization. Practical guidance on choosing warm-up duration is provided in the appendix. Understanding the robustness of the failure boundaries location to dataset and architecture changes could provide insights into the success of heuristic learning rate choices based on past experience. Our experiments were limited to small-scale datasets and models, so further research is needed to confirm our findings on larger scales. For Adam Optimizer, we did not explore the impact of hyperparameters like beta 1, beta 2, and epsilon.